Good day, my name is Tubeshe Spanda. Welcome back to another Fluid Mechanics 101 presentation. Today I've got a flow, so don't mind my sniffings. So today I'll be doing a presentation which is more inclined to civil engineering. So bear with me for those who are not civil engineers. So the energy current line shows the total energy, which is pressure, velocity, and elevation, if you know your Bernoulli equation, while the hydraulic current line shows only pressure and elevation energy, excluding velocity. So it only shows, the hydraulic current line only shows what the pressure gauge will read. The energy current line lies above the actual pipe or channel profile. I will show you what I mean as we proceed with the presentation. The hydraulic current line shows the pressure and the elevation energy only. It does not include the velocity head. It represents the height to which the fluid will rise in a piezometer tube inserted into the pipe or channel. We use the piezometer tube to measure the static pressure using the height to which the level will rise in a pipe. This line is always below or equal to the energy current line. If the velocity is 0, which means the fluid is not in motion, you only have static pressure, then the hydraulic current line and the energy current line coincide. In open channel flow, the hydraulic current line is equal to the free water surface, which means the line will follow the free water surface because there's no pressure, right? So this is for open channel flow. You see, this is your bottom pipe, which is the top of the pipe. So which means this is your level of your liquid, whatever liquid is flowing in your pipe. Then your hydraulic current line, you see, it follows your free water surface. But your energy current line is above, which means it's higher. But for a pressurized pipe, this is the bottom of your pipe, this is the top of your pipe. Because it's pressurized, then your hydraulic current line is above. Then the energy current line is above the hydraulic current line. Tight line operation. When there are drastic elevation differences in a long pipeline, let's say your pipeline is going over mountains and stuff, sometimes the last section of the pipeline towards the delivery terminus may operate in an open channel flow, which means that section which is higher when it's flowing downwards, it will flow in an open channel. This means that the pipeline section will not be full of water and there will be a vapor space above the water. Such situations are acceptable in water pipelines compared to high vapor pressure liquids such as liquefied petroleum gas, because those ones are volatile, so it might cause some fire hazards, so it might cause a pipe burst. So we always try to make sure that our flowing pipes, it's tight line operation, which is it flows fully. To prevent such open channel flow or slack line conditions, sometimes it's called slack line flow, we peg the line by providing adequate back pressure at the delivery terminus as illustrated in the figure below, which means you make sure your delivery pressure is high so that there's big pressure to push your hydraulic current line above this peak. But once it comes below this peak, which means now you have a slack flow here, most probably it will correct itself here and start to have a tight line flow here. Slack line flow, slack line operation. Slack line or open channel flow occurs in the last segment of a long distance water pipeline where a large elevation difference exists between the delivery terminus and intermediate point in the pipeline as indicated in the figure below. As I said, you see this is the highest point. So at this point up to here, we have an open channel flow where your where your hydraulic grid line, from here it will come up to the point, then just follow the surface of your water as I showed you initially. Here it corrects itself, then it becomes a tide line flow, or the pipe becomes full again due to back pressure, because by this change of elevation, then your hydraulic grid line will be above your pipe profile. If the pipeline were pegged to avoid slackline flow, the hydraulic gradient is shown by the solid line in figure above. So right, let's assume we peg it, right, which means we increase our pressure up to here, which means our hydraulic line will be straight like this, come till it joins this line. Okay, so which means we have pegged that line, which means we increase our pressure here, because now you see our pressure is low. But if you increase it up to there so that we have this back pressure, then our line will be tight packed. However, the piping system at the delivery terminal may not be able to handle the higher pressure due to line pack. But what if then this pipe which you're using here cannot handle the high back pressure? Therefore, we may have to reduce the pressure at some point within the delivery terminal using a back pressure control valve. That's what we did here. We just put a valve to create that back pressure, which means your line will come like that. But since it reaches here, we'll put a valve to create this back pressure or back flow. So it will come here we have this sudden drop due to pressure drop due to a valve. Then it cross like this. So this is your back pressure. Hydraulic gradient. The graphical representation of pressures along the pipeline, as shown in figure below, is called the hydraulic pressure gradient, which means you're just this is the pipe profile, the elevation, starting from 0. So your profile goes like your pipe profile. Let's say there's a mountain here, or I don't know what it is, then your pipe profile is to follow it, go up. You don't want to dig through that mountain or whatever it is. Here there's a value there, therefore it will follow that value, right? Yes. So this is just the this is the plot of pressure, which means you measure pressure here, you get the value in feet, you plot it here. Same applies to here, you plot it there, plot it there, plot it there. That's what that line is. Okay, since elevation is measured in feet, the pipeline pressures are converted to feet of head and plotted against the distance along the pipeline, superimposed on the elevation profile. If we assume a beginning elevation of 100 feet, a delivery terminus elevation of 500 feet, a total pressure of 1000 psi required at the beginning, and a delivery pressure of 25 psi at the terminus, we can plot the hydraulic pressure gradient graphically by the following method. So at the beginning of the pipeline, the point C representing the total pressure will be plotted at a height of, which means, remember, we said the pipe is 100 feet above the ground. Then we need a pressure of 1000 psi. So we want to convert this to feet too. So we multiply by 2.31, so we get 2,410 feet. Similarly, at the delivery terminus, the point D representing the total head, a delivery will be plotted at a height of, we said it's 500 feet above the surface. Then we want a pressure at the delivery terminus to be 25 psi, converting to feet. We get the total is 558. The line connecting the points C and D represents the variation of the total head in the pipeline and is termed the hydraulic gradient. So this is C, you got that value, plot it here, you got the value, so it represents the hydraulic gradient. All right. At any intermediate point such as E along the pipeline, the pipeline pressure will be the difference between the total head represented by point F on the hydraulic gradient and the actual elevation on the pipeline. So we are saying the pressure here. What's the pressure at this point? So is this pressure F? You read it here in feet minus you read it E. So the difference, that's the pressure within the system at that point. If the total head at F is 1850 and the pipeline elevation at E is 250 feet, the actual pipeline pressure at E is that of 1850 minus 250 feet, which is 1,600 divided by 2.31 to convert this feet to PSI. It can be seen that the hydraulic gradient clears all peaks along the pipeline, which means our pipe will flow fully throughout the length of the pipe. If the elevation at E were 2000 instead, we would have a negative pressure in the pipeline at E equivalent to that minus 65, which means now at E your graph, this one will be below this one. It will cut like this. Then remember, whenever that hydraulic grade line passes under your pipe elevation profile, which means we have a slack flow, which means some part of that pipe, wherever it's the hydraulic grade line is below the pipe profile, then we have a slack line flow. It will be flowing partially. Since a negative pressure is not acceptable, the total pressure at the beginning of the pipeline will have to be higher by the preceding amount. So we need to add that 65 psi, which is 150 feet, right? We add it back so that you lift it up. This will result in a zero gauge pressure in the pipeline at peak E. The actual pressure in the pipeline will therefore be equal to whenever the gauge pressure is zero, which means your pipeline is close to atmospheric pressure, right? So the actual pressure in the pipeline will therefore be equal to the atmospheric pressure at the location, since we would like to maintain some positive pressure above the atmospheric pressure. In this case, the total head at A must be slightly higher than 2,560 feet. You always want your pressure to be higher so that you can detect leaks and stuff instead of you pulling water inside. Let's say there's a leak you want to spray outside. Assuming a 10 psi positive pressure is desired at the highest peak, such as E, 2,000 feet elevation, the revised total pressure at A will be that. So you add that 10, so that 1075, so that you have a tight line flow. Therefore, total head at C now will be 2,483. This will ensure a positive pressure of 10 psi at the peak E. Remember, you want it to be above. So that's one. Gravity flow in water pipeline occurs when water flows from a source at point A at a higher elevation than the delivery point B without any pumping pressure at A and purely under gravity. This is illustrated in the figure below, which means if my tank A is above 10 B, I can actually transfer the liquid from this one to this one just by using gravity. There's no need for me to use the pump. But the question is, how long will it take to empty this tank to this one? Or what will be the flow rate? Q. So the volume flow rate under gravity flow for the reservoir pipe system shown in the figure above can be calculated as follows. If the head loss in the pipeline is H feet per feet of pipe length, the total head loss in length L is that. So which means it's your head loss per feet multiplied by this length. Right? Since the available driving force is the difference in tank levels at A and B, we can write H1 minus this head loss times length of the pipe will give via H2, right? Therefore, HL is equal to H1 minus H2 using a mathematical manipulation. H is equal to H1 minus H2 over L, where your H is your head loss in pipe. Feet per feet length of pipe, which head in tank A, head in tank B. In the preceding analysis, we have neglected the ingress and exit losses at A and B. Remember, if you remember on my other presentations, if this fluid is entering this pipe, there's a head loss there. There's also a head loss due to fluid flowing along this pipe, and also head loss as this liquid enters B, but they are usually minor, so that's why they're usually neglected or not included in the calculations. In the preceding analysis, we have neglected the ingress and exit losses at A and B. Using the Hazel-Williams equation, you can then calculate flow, right, based on C value. Also, I have shown you the Hazel-Williams equations on the previous presentations. So, an example, the gravity fixed system shown in figure above consists a 16-inch pipe in all thickness, 3,000 feet long pipeline with a tank elevation A 550, elevation B at 150. So this one is 550 side, 150, 3,000 long, right? Calculate the flow rate through this gravity flow system using the Hazel-Williams equation, Williams C factor of 130. So we want to calculate the head loss in feet per feet. So 500 minus 150 divided by the 3,000, which is the pipe length. You get it 0.1167 feet per feet, substituting the Hazel-Williams equations. So we multiply by 1,000. If you remember the Hazel-Williams, it calculates per 1,000 feet. So that's why we are multiplying by this 1,000. This is just a constant. This is your Q, your flow rate constant, which is your internal pipe diameter, a constant. So solving for flow rate Q, we get that our Q is 15,484 gal per minute. So that's the flow which you get there. Okay, this one. Okay. Okay, so now compare the results using the COLE-BROOK White equation, assuming E. Remember, we say the value of that roughness is usually in this value. If you remember my previous presentation, so using the diameter, you can get the absolute roughness. So that's the roughness of the pipe. So the absolute roughness divided by the diameter. You get that. We'll assume a friction factor of F is equal to 0.02 initially, head loss due to friction. We calculate, we end up, if you simplify, because we don't know the Q, right? We don't know the Q there. We have assumed this loss by using this calculation, right? Friction loss. Then you calculate your Q, get to be almost 13,000 gal per minute. Solving for Reynolds number, 2,600 from the multi diagram F. Now we recalculate. We get that expression. Okay, solving for Q again, you get that by successive iteration, you arrive at the final flow rate of 16,379 gal per minute using the COLE-BROOK White equation. Again, if you forgot how to use this method or calculations for your flow rates, you can go back to my previous presentations. Here I just zoomed past through because I already spoke in depth on my previous presentations. So comparing with the 15,484 gal per minute we got using the Hazel-Williams equations versus the 16,000 using the COLE-BROOK White equation. So we see that the flow rate is underestimated because the assumed Hazel-Williams C factor was too low. So it's, if you are not familiar with your system or your pipe system, I would advise I would advise you use the COLE-BROOK White equation instead of the Hazel-Williams equations, since it gives a more accurate figure or calculation. But let's say now you're used to your pipe, like firefighters. Now they know this effect of their system, so they can actually use the Hazel-Williams equations because it's easier to use, easy and fast. Another example again, the two reservoir system described in last example is modified to include a second source of water from a tank located at C between the two tanks located at A and B away from the pipeline AP. The tank at C is at an elevation of 3,000 feet and connects the piping from A to B via a new 16-inch 1,000 feet long pipe. CD, the common junction D is located along the pipe AB at a distance of 1,500 feet from the bank at B. Determine the flow rates Q1 from A to D, Q2 from C to D, Q3 from D to B using the Hazel-Williams equation with the C factor of 1/3. So I drew the schematic so that it becomes clear, but here I made the mistake. This is 500 feet, which means it's actually higher. This is the Migley pipeline which we have added to the previous system, so it's somewhere here. This is a bit higher because 550, 300 feet. So it joins this pipeline in the middle. And everything else remains the same. So we are asked to determine the flow rate Q1 from A. So you want to know what are the new flow rates Q1, Q2, Q3, right? So at the common junction D, we can apply the conservation of flow principles as well, which means that here, with Q1 plus Q2 is equal to Q3, whatever comes combines, right? Also, since D is a common junction, the head HT at point D is common to three legs AD, CD, and DP, meaning whatever pressure remaining is here, there will be a pressure loss. But once it gets here, because it's the same point, which means it will have the same head. It's the same height, right, from a certain elevation, or it's the pressure here for a gauge is the same, right? So which means whatever pressure is here, there will be some pressure loss here, but once it reaches here, it will have the same peak because it's a common point, right? I put a gauge there, I get the same pressure. I hope that makes sense. Designating the head loss due to friction in the respective pipe segments AD, CD, and DP as HFAD, HFCD, and HFDP, we can write the following pressure balance equation for three pipe legs. HD, so HD at that point was to, as I was saying, HD is same as HA minus HFAD. This is point D, I forgot to mark it. Also, HD is equals to HC minus HFC. I had some internet issues here. So HD will be that HC, HB, we're adding back the friction loss because we're going backwards. Since the pipe sizes are all 16-inch and the C factor is 1/3, using the Hazel-Williams equation, we can write HFAD, this is just a constant, it's length LAD per 1,000 feet, which is your Hazel-Williams equation, your flow rate, your C factor, your constant, which is the internal diameter. So lumping all these terms together, because they are constant, right? We get a KLAD K1 to the power of 1.852, where K is a constant for all pipes and is equal to that K you calculate, which means to simplify this, you get 2.0305 by 10 to the power 9. LAD, length of pipe from A to D, which is 1,500 feet. So now we can write HFCD for FCD equals to K. The only thing we change is LCD, right? And for leg DP, we do the same thing. So substituting the values in the preceding HD equations. If you remember, we have these equations there. So let's put those values back. You get HD equals to 500 minus K by 1,500 times K. 1 to the power 1 8.582. Same applies to the other legs too. For Q2, Q3, simplifying these equations by eliminating HD, which means if I say this equation is equal to this one is equal to this one, I come up with these two equations, right? Also, because now we have two unknowns here, we need one more. Well, we have three unknowns, so we need one more, three equations to fully specify our problem, right? So we have this one, Q1 conservation of flow, Q1 plus Q2 equals to Q3. So substituting the three flow rates, we get Q is equals to Q1 equals to 16.677, Q2 is equals to 1000, and Q3 is equals to 17,6777. I suggest you follow the math and do it yourself so that it makes more sense. But obviously the Q2 was I will go back here. You see Q2, it's a bit higher. The flow rate it's higher than Q1. Why? Because the head loss. Remember, this is shorter, so which means there's head loss. It's not much as compared to this one. So obviously, it will contribute more flow as compared to this one. Okay, thank you for watching. If you have any questions and additions and subtractions, do not hesitate to contact me on my email address toolsfund@gmail.com. Please like, subscribe to my YouTube channel to learn more data engineering stuff. Next, I'll be talking about how to size pumps, how to size the motor pump, and stuff like that. So stay tuned to learn some more stuff. See ya. Okay.